Now we will introduce the subgroup generated by subset. Subgroup generated by subset. Suppose G is a group. Suppose G is a group that G is a group. And I take a subset, let S be a subset of G and non-empty subset. This set may be finite, this set may be infinite also. Okay. Then define a set. Let us denote this set as angle bracket S. We are defining this set to be the elements of the form A1, alpha 1, A2, alpha 2 up to An alpha n, such that Ai belongs to S. N is some natural number and alpha I is integer. What does it mean? Let me first explain it by example. Suppose I take S3. S3 has how many elements? This 1, 2, 3, 1, 3, 2, 1, 2, 1, 3, 2, 3. These are 6 elements of S3. And suppose I take a subset S to be this and suppose I take subset to be 1, 2 and 1, 3. I take 2 elements. Now what do you mean by this subset? This subset, the powers of here are actually the integers. So we can put all the powers 0. So it means A1 to the power 0, A2 to the power 0, An to the power 0 means identity, identity, identity. Also this n is a natural number, so n can take value 1 also. So single elements and all its power will be inside this set. So single element and all its power, so 1, 2 to the power 0, 1, 2 to the power 1, everything will be here. But 1, 2 to the power 2 is again 1, 2 to the power 0, so there is no need of writing. Similarly 1, 3 to the power 0, which is again identity, equal to this. So in a set both are equal, and 1, 3 to the power 1 is also here. Now all the products, so 1, 2 and 1, 3's product will be here. So what types of product? 1, 2, 1, 3 or 1, 3, 1, 2, this type of product, or any another type of product, that is 1, 2 to the power some integer n1 and 1, 3 to the power some integer n2 will be here, or in another way 1, 3 to the power n4 and 1, 2 to the power n5 will also be here. So after that I am writing element here, or any another combination like 1, 2, 1, 3 and 1, 2 again, this type of combination or any another possible combination will be here. So this may be n6, n7, n8. So all this type of combinations will be here. Let us think about it. What is 1, 2 to the power 0? 1, 2 to the power 0 is identity. So this 1, 2 to the power 1 is 1, 2. 1 3 to the power 0 mean identity, it is written here 1 3, this is 1 3. What is 1 2 1 3 composition? So 1 is going to 3, 3 is going to 3, so this is 1 3 2, one can check. And similarly this is 1 2 3, like this. Okay. Similarly, you can calculate all these numbers for integers. For all these integers, we can calculate these numbers, and these numbers and these numbers. But note one thing, that S3 has only 6 elements, and out of that we have found 1 2 3 4 5 elements. And this, whatever the subsets we are going to create, whatever the elements will come here, that is a subset of S3. This will be inside S3. Now one thing you can note, that 2 3 can be written as 1 2 1 2 1 3 1 2. Is it clear? 1 is going to 2, 2 is going to 2, 1 is going to 1, so 1 is going to 1, 2 is going to 3, and 3 is going to 2, so 2 3. And this combination will also be in this combination, like here. So it means 1 2 3 will also be here, so this subset will become S3. So for example, this set, in this set case, this is S3. So it means whatever the powers remains, because of the binary operation, this composition will lie in this set, and this set is covering the whole S3. So it means all these powers will be out of these elements. So this was an example. If I am taking this as a subset, then we are to consider all the powers of this subset, of the elements of this subset. Now again, suppose I take another subset to be 1 2 3, then we have to take all the powers of 1 2 3, and the product of all the powers of the elements of this subset. So whatever we will get is that we will get actually 1 2 3 some n1, and the another element when you will choose it is again 1 2 3, so that may be n2, or if you want to repeat, then again some elements here you can take, but that element will also be 1 2 3. So it means every time you have to take 1 2 3, so simply we can write 1 2 3 to the power n, such that n belongs to Z. That is, the elements of the form identity 1 2 3 and 1 3 2. So like this we can write. Okay, now this was just an example that if you take two elements and want to calculate this set, then what will happen. So for example, in this case it turns out to be S3, for this case it turns out to be this set, and for different sets it will have different values. Now we will show that this is a subgroup. We will show that this is a subgroup of the group G. So my claim is that this set is a subgroup of the group G. Okay. So for showing the subgroup, what we have to show is that we have to show that it is non-empty first of all. So note that S is contained in this set. S is contained in this set. Why? Because take any element in S, then this implies A can be written as A to the power 1, and any element to the power something of S will lie on this set. So this belongs to this set. So this set is actually non-empty. So this set is non-empty. So thus this set is not equal to 5. Also, for A in S, A to the power 0 belongs to this set. This implies identity of the group belongs to this set. So identity is also here. Now suppose I take two elements from this set. Take one element to be A is equal to A1 to the power n1, A2 to the power n2 up to A n to the power, let me take alpha 1 here, alpha 1, alpha 2, alpha n. In this set, and take another element B is equal to some B1 to the power beta 1, B2 to the power beta 2 up to Bk to the power beta k in S. Sorry, Bk. So this is Bk to the power beta k, where this Ai's and beta i's belongs to S. And alpha I, what are alpha I and beta I? These are integers. And what is n and k? These are natural numbers. Now what is AB? Means A operation B. The operation is of the operation of the group G. This is A1 alpha 1 up to An alpha n, and then B1 beta 1 up to Bk beta k. Now thing is that whether this element belongs to this set or not. I am saying that this set consists of all the elements of this form, where this n is a natural number. So here there are n elements and then k elements. So n plus k is a natural number. This is the set of all finite products. Finite why? Because these are n in numbers, set of all finite products, and where n is also varying. So product of one element, product of two element, product of three element, product of any number of n elements, finite product is always here. And this is the product of n plus k element. Another thing is that power should be integers. So all the powers are integer, you can see. And whatever is written in the base should be an element of S. All the elements written in the base are elements of S. So it means this element is also of this form, so it will belongs to this set. So this belongs to this set. Now further, if I take A to be this element, then what will be A inverse? By definition of inverse, we can see 2 alpha 2 dash 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 An alpha n. The inverse is inverse of this element. We know that AOB inverse is B inverse OA inverse. So the inverse will change the elements, and we can write it as An alpha n inverse up to A2 alpha 2 inverse and A1 alpha 1 inverse. But inverse of the power mean An minus alpha n up to A2 minus alpha 2 and A1 minus alpha 1. Now because alpha 1, alpha 2, alpha n are integer, so minus alpha 1, minus alpha 2 and minus alpha n is also an integer. So this element is again of this form. So this simply means that this belongs to this set. So what we have shown is that this set is non-empty. Product of two elements will belongs to this set, and the inverse of an element also belongs to this set. So hence we have shown that this is a subgroup of the group G. This is a subgroup of the group G. Is it okay? Now there is one more thing in this subgroup, and the special thing with this subgroup is that S is contained in S. S is contained in S. This subgroup is called the subgroup generated by the subset S. So let me do it. This is called the subgroup generated by subset S. One simple observation is here. Suppose H is a subgroup of a group G, and S is contained in H. Then my claim is that, okay, let me not write claim. If S is contained in H, then what will happen? Then for A1, A2, AN in S, which is contained in S, which is contained in H, so this A1, A2, AN are elements of H. So any power of A1, any power of A2 and any power of AN will also be an element of H. So this implies A1 to the power alpha 1, A2 to the power alpha 2, AN to the power alpha n will also be an element of H. Because A1 to the power alpha 1, A2 to the power alpha 2 and AN to the power alpha n belongs to H, so it simply means that their product will also belongs to H. This simply implies that A1 to the power alpha 1, A2 to the power alpha 2 and AN to the power alpha n will also belongs to H. So any element of this set will belongs to this H. Is it okay? If S is contained in H, then this type of element will also contain in H. This simply implies that this subgroup will be inside H. So we can say that S has property. So what we have observed is that one thing, that this is a subgroup. Second thing, we have seen that S is contained in this subgroup. And third thing which we have just now observed is that if S is contained in H, then this is also contained in H, where H is a subgroup of the group G, where H is a subgroup of the group G. So we can say that this is the smallest subgroup containing S. Why smallest? Because any subgroup which contains S will also contain this subgroup. So we can say that this is the smallest subgroup containing S. Is it okay? Now I will describe this thing in another way. So let us do it in another way. Okay, now I will tell you the intersection of two subgroups. intersection of two subgroups. Suppose H1 and H2 are two subgroups of a group G. H1, H2 are two subgroups of a group G, and I take their intersection, take H to be H1 intersection H2. We will show that this H is a subgroup of the group G. So how? Now since H1 is a subgroup, so E belongs to H1 and also E belongs to H2. So E belongs to H1 intersection H2 because E is in both the set, that is H. So this proves that H is non-empty and identity element belongs to the H. Now take two elements AB in H. Then what will happen? This implies A comma B belongs to H1 intersection H2. So this implies A comma B belongs to H1 and A comma B belongs to H2. But H1 is a subgroup. It implies A composed with B inverse belongs to H1 and A composed with B inverse belongs to H2. And because A composed with B inverse is in both the set, so it implies that this belongs to H1 intersection H2. Hence H1 intersection H2 is a subgroup. That is equal to H also. So intersection of two subgroup is a subgroup. If I take two subgroup and take their intersection, then it is again a subgroup. Okay, now I want to say that you take any number of subgroups and intersect them, you will get a subgroup. So I will write it as intersection, arbitrary intersection of subgroup, intersection of subgroup subgroups. We will show that arbitrary intersection of subgroups is a subgroup. Arbitrary intersection means the set of subgroups may be finite, the set of subgroup may be infinite, and in infinite it may be countably infinite or uncountably infinite. So how to write these things? So let us choose a set which is called indexing set. And let me call it A. What does it mean? Now I will say that how many elements, I will say that for each element of A there is a subgroup. So consider a family B of H alpha such that alpha belongs to A, where H alpha is a subgroup of a group G. This is just a way of writing the things, because we have several cases, and in this way when we will write, this will cover all the cases. For example, suppose this set A, which I am calling as indexing set, A has 1, 2 elements. Then what about B? This B has H1 and H2, 2 elements. So means 2 subgroups we are considering. Suppose A has elements 1, 2, n, then it means this B has elements H1, H2 and H alpha, Hn. So it means we are caring for n elements. These are n subgroups of the group G, and suppose A has infinitely many elements dash dash and so on. So that simply means this is equal to the set of natural number. Then B is what? H1, H2 and so on. So B has infinitely many elements. So this B has infinitely many elements. Suppose now A is equal to R. This means what? B is H alpha such that alpha belongs to R. So how many elements does this B have? This B have countably infinite element, uncountably infinite element, and for each symbol from this set, that is R, we have a subgroup, and that subgroup is denoted as H alpha. So actually we are not able to write it in this way or any another way. So what we have done is that we have associated a set, that is indexing set, such that for each element of this set we have a corresponding element, corresponding subgroup of some group. So this is just a way of writing. So when we write in this way, this will cover all the cases, either the case of 2, case of finite, countably infinite or uncountable infinite. This B will cover all the cases here. So this was just an explanation. Now we will prove. Now we will prove that the intersection of all the elements of B are subgroup. So take H to be the intersection of H alpha such that alpha belongs to A. Means if we have 2 elements, then H1 intersection H2. If we have n elements, then it is H1 intersection H2 up to Hn. If we have this many elements, then H1 intersection H2 and so on. And if we have this many elements, then intersection H alpha, alpha belongs to A. So in this way you can take the intersection of all the elements of B. So clearly H is the intersection of all the elements of B. Now the pattern of the proof is same. Let me rewrite it. We will do the same thing here for proving it. So let me rewrite this thing. So since E belongs to H alpha for all alpha in A, so E belongs to H, which is intersection of H alpha, alpha is in A. Because E is in each of this H alpha, so it will be in the intersection. So this H is non-empty. Now take 2 elements AB in H. This implies AB is in the intersection, So AB will be in H alpha for all alpha in A. Now because H alpha is a subgroup of the group G, so AOB inverse belongs to H alpha for all alpha in A. This simply implies that AOB inverse belongs to intersection of H alpha in A, because this is in each of H alpha, so it will be in the intersection which is equal to H. Hence H is a subgroup. H is a subgroup of the group G. So take whatever the number of subgroups, take their intersection, that will again be a subgroup of the group G. But this is not the case with the union. For example, let me tell you, union of subgroup need not be subgroup. Subgroup need not be subgroup. For example, take Klein's 4 group V4 is equal to E, A, B, C. I take one subgroup H1 to be E, A, and I take another subgroup H2 to be E, B. Let us take their union, H1 union H2. This will be E, A, B. But this is not a subgroup because inverse of each element is here, it's okay. Identity is here, it's okay. But what about AOB? AOB is C, and C does not belongs to H1 union H2. So it is not a subgroup. So it is not a subgroup of V4. This notation is for not a subgroup. So H1 union H2 is not a subgroup of V4. So union need not be a subgroup, but arbitrary intersection is a subgroup. So take any number of subgroups and intersect, take their intersection, that will again be a subgroup of a group. Okay. Now I am going to define a set. Okay. Now consider a subset S of a group G, that is S is contained in G. Take a family B of H subgroup of G such that S is contained in that subgroup H. So what we have done, we have taken a subset S of a group G. So S is a subset of a group G, that is S is contained in G, and now we consider a set capital B of those subgroups of G. So the elements of this capital B are the subgroups of G such that S is contained in that subgroup H. Now consider some H to be the intersection of all the elements of B. So how will we take intersection? So let me call it H1 to be the intersection of H such that H belongs to B. So this is the set of subgroups and H1 is the intersection of all the subgroups. So just now we have proved that this intersection will be a subgroup. So clearly H1 is a subgroup of the group G. Since S is contained in H for all H in B, so S will be contained in H1. Now one question that may arise is that there may be not any subgroup which contains S, but that is not true because S is contained in G and G is a subgroup of G. So at least one subgroup is there in this B, so G belongs to B, that is improper subgroup. So this set B is actually non-empty set. This set is non-empty because G will always belongs to this set. So whenever you will take intersection, at least one element will be here. So this H1 will exist because if there is not any element, you will take intersection, you will get nothing. You will get phi, and phi is not a subgroup. So this H1 is a subgroup because B is non-empty. Now if H1 is a subgroup, then this subgroup will contain S. So H1 is the subgroup of G containing S. Also H1 has a special property. What is that property? If S is contained in H2 for some H2 for some subgroup H2 of G, suppose, then what will happen? Then this H2 will belongs to this family B. This implies, because it is in the family, so this H2 will come here. This implies intersection of H such that H belongs to B will be contained in H2. Because H2 will also come here, so it means H1 will be contained in H2, that is H1 is contained in H2. So this means if S is contained in H2 for some subgroup H2, then H1 will contained in that subgroup H2. Okay, but we know that S is contained in this subgroup. This implies H1 is contained in this subgroup. But we have shown one more thing, that the same property, this subgroup has the same property. That's why it is called the smallest subgroup. Since S is contained in H1, this implies the subgroup generated by S is also contained in H1. Hence, this is equal to H1, that is intersection of all the subgroups which contains S. So the subgroup generated by S has two different explanations. One explanation is that how will you generate a subgroup by S? One explanation is that you take all the subgroups which contains S and take their intersection. You will exactly get a subgroup which is generated by S. The another explanation is that you take all possible finite linear combinations of, you take all possible products of elements of S, and that will give you the subgroup generated by S. Okay, so let me write it what I tell you just now. So subgroup generated by S has two explanations. Subgroup generated by subset S. I am denoting it as this. So it has two explanations. One explanation is that it is the set of elements of the form a1 to the power n1 up to ar to the power nr, such that r belongs to n, ni belongs to z, and ai belongs to s. This is the set of all products of this form. These are the product of finitely many elements. Infinite product will never come. Now, the another explanation is this is the intersection of all subgroups which contains S, where B is the family of subgroups, H is a subgroup of G, such that S is contained in H. So these are the two explanations of this same set. So subgroup generated by a subset S mean this thing or these things.